background was in the history of science, the history of astronomy as well as science. It speaks to me about the history of our understanding of the Magellanic Clouds, and because, as the author tells us with the title of it, Henrietta Swan Leavitt and the Magellanic Clouds, it speaks to me about Ms. Leavitt and about women in her era, her era having been like the turn of the 19th century into the 20th century, her era at Harvard College Observatory, where they hired a surprisingly large number of women to do what I kind of think must have been the grunt work of astronomy, not the high prestige in the telescope at night kind of work, but because they had photography available and you could bring a picture, you could bring an image into the observatory, then you could have day work. You could have nicely chaperoned groups of women sitting in tightly laid out desks working on something. And some of these women had no background. Some of these women, like Leavitt, had essentially two bachelor's degrees. And they were doing this stuff that basically the guys didn't want to do. And they turned astronomy into astrophysics. This isn't too different from the way the Magellanic Clouds look. She says she's trying to get the right, she says, density of stars, but they're not exactly a star here versus a star here versus a star there. They're about the right number with about the right scattering of little ones and big ones, which would be like dim ones and bright ones. So it's interpretive, yes. It's absolutely an interpretation of a photograph. Claim to fame, we've never said this, so we should really say.
Tell me more about
Henrietta
her.
Leavitt's specific claim to fame is that she discovered a kind of star called a Cepheid variable star, which gets brighter and dimmer. If you graft its light, it gets bright and dim in a very regular way. And how fast that happens, the period between bright, dim, bright again, tells you how bright the star really is. And that's a challenge because when you look out in the night sky, you don't really know how far away things are. So you don't know if something is bright because it's close up, or if it's pretty far away and it's just really super bright. So her discovery of the period luminosity relationship for Cepheid variable stars was this fantastic calibration tool that let you say, yes, this thing, it's really that far away. And it was the first time people were able to measure distances beyond really close distances that spanned the size of our Milky Way galaxy, and then that showed you that there were things farther away. That squidgy little faint fuzzies out there, like the Magellanic Clouds and the Andromeda Nebula. People knew they were there. They were faint fuzzies. What are they? Are they close up? Are they far away? That they are galaxies, in the case of Andromeda, comparable to our own, incredibly far away. And that really gave us, for the first time, like about 1920 or so, 1920, 25 or so, true understanding that galaxies are a structure in the universe, we're in one of them, and there are uncountably many farther away that are galaxies comparable to our own and unspeakably distant. And we're still finding that out every time we get a new piece of technology, like James Webb, the brand new telescope of just a few years ago, that there are yet more of them, yet farther away, and the universe just keeps getting bigger and bigger. The universe we know keeps getting bigger and bigger.
It's so humbling, isn't it?
It's humbling. But you know, it's humbling on one level, and yet you gotta think the human brain. Does anything reach far? Nothing we know reaches farther than the human mind, so we should be humble about our physicality. Not that it isn't important, it's just, it's humbling. But the grasp of our questioning, I mean, I wouldn't say our understanding, I would say our questioning. The grasp of our questioning is infinite. That's what powers me sometimes when things aren't great. That thing is enough to power me.
I follow you. You know, we were talking about earlier is that, you know, the thing about our disciplines is that I think we both ask questions more than present answers, or at least as an artist, I feel like it's more to ask than it is to answer. The whole process of putting together this Seeing the Unseen exhibit
let me, first of all, spend time with some colleagues. I knew they were interesting, and until we were talking about this, I didn't really know how interesting what's going on in all of these brains around chafing. And actually, the most interesting part that is common to the science and art is just what you said. It's the questions we ask. The answers are cool, but the questioning is the part of the process.
And I like bringing that up because I feel like many of us feel separated within our disciplines. Like, what is an artist going to have to help me in astronomy, right? And
infinitely much, it turns out.
Well, of course.
In the process of finding artists for this exhibit, we found so many places, so many pairs or larger groups where an artist and a scientist were working together.
Oh, good.
And where what the artist does representing something, I guess the two I'm thinking of are examples in which the artist has come to work in the science lab for a while and represents something about the science, and then the scientist takes a look at the way the artist represents the science and says, oh my God, there's this thing I didn't see. I think there's so much more here. I think it can and should happen more often that we sort of trade representations with each other. I mean, see more.
Is this an actual image from the past? Like,
no, as I understand it, what Halloran does, and she's done this with quite a large number of historically important astronomical photographs on glass plate, about a foot square. And these would have been taken in an observatory at night with what was then a high quality telescope. And these things were then brought back and stored and used. And
that's when they studied them.
And that's when they studied them. Now, what Halloran has done is she's looked at the photographs. The one she's looked at, she's done an amazing job of capturing a bit more abstractly, painting, repainting, but on this much huger scale, paints that as a negative and then makes a cyanotype out of it. And it goes beyond this historically important, but maybe if you aren't into it, kind of boring black and gray thing like this, into this enormous blue and white thing that is much more exciting to look at. And,
Can I ask one question?
Sure.
That might be a little bit far out, but you were talking about the body. We're talking about the galaxies and the numerousness of them. Is it possible that our bodies are made out of space dust and space particles?
Absolutely, it is. It is exactly as Carl Sagan said. We are made of stardust.
Wow. Okay.
We are made of stardust because everything other than hydrogen, helium, and a tiny amount of lithium. That was what was made in the Big Bang. Everything more complicated in all the world around us, but in you and in me, in our bodies, is made in the interiors of stars, or else made in the kind of explosive death throes when a giant star comes to its end. And that's the nucleosynthesis that makes everything, the carbon, the nitrogen, the oxygen, the iron, the everything that life has. Because you wouldn't, maybe this is a failure of imagination, but most biologists or astrobiologists can't imagine how you could make anything as complicated as life out of hydrogen, helium, and a little bit of lithium. All the subtle organic chemistry complexity seems to depend on more complicated, heavier, bigger elements, and stars are what make them. Stars are what make them. Galaxies are what hold it together so it isn't just sort of spewed out everywhere.